Last little tidbit before we get into moving things across epithelial membranes is just to give you guys the opportunity to sort of quiz yourself and try to see if you've figured out how to predict how things get across cell membranes. So we're going to go through G right here. How would each of these substances cross the cell membrane? It's really important that you don't just rote memorize this. You need to understand why it would cross that way and what type of transport protein it is and what the transport is actually called. So we're going to practice this a little bit. So I'm going to do it on a whiteboard. Okay, so here are our challenges. Number one is, okay, so let's just make this ECF and ICF arbitrarily. Doesn't really matter which one's which. And this yellow represents the cell membrane here. So the number one asks, oxygen is moving down its concentration gradient across a plasma membrane. What kind of transport mechanism can that use? Is there a transport protein? Is there any energy required? So let's say we've got high oxygen here and low oxygen here, which is generally going to be true, and especially when cellular respiration is active. So how is it going to move across? Well, it wants to move straight across, and that's all well and good. And it can, because oxygen, of course, is lipid soluble. What type of transport is this? This transport is simple diffusion. Okay. And does it need a transport protein? No, it doesn't, because it can diffuse straight through the plasma membrane. So this is simple diffusion. Okay, so number two says potassium is moving down its concentration gradient. So potassium is going from high potassium to low potassium. Okay, so I don't know if you guys remember this, but hopefully you do. So potassium is high here and it's low here. And so how is it going to move? Well, can it move directly across the cell membrane? It can't. Who remembers why? Why can potassium not move directly across the cell membrane? Because it's a charged or polar molecule, and so it's lipophobic and hydrophilic, but it can, if you give it the opportunity, move through a channel. So potassium can move through a channel. What is this? This is diffusion. It's not simple diffusion. It's diffusion, I would call it diffusion through a channel. So that's number two. Okay, number three says an amino acid moving across a plasma membrane into a cell for protein synthesis. Okay, an amino acid. Hopefully you guys remember that those are mid-size. They're much bigger than O2 or a K plus ion. Okay, and it is going to move across a plasma membrane into a cell for protein synthesis. So how do you move mid-sized water-soluble molecules? So I've got an amino acid. Okay, it wants to move in, and let's say its concentration gradient favors it moving in. But can it move straight through the cell membrane? Nope, too big. Can it move through a channel? No, it's generally too big to move through a channel as well. So what do you do next? Well, I'm going to move it through, let's say it has this shape, the carrier has this shape, and it's going to move through the carrier protein. What is it called when you diffuse something from high concentration to low concentration through a carrier protein? This is number three, and it's called facilitated diffusion. Okay. Number four, a large antibody protein made by a white blood cell is going to be secreted. It's a big protein, so it's a large water-soluble molecule. How the heck are you going to get that to go through? Can it do simple diffusion? No, way too big, and also water-soluble. Can it go through a channel? No, too big. Can it go through a carrier? It may even be bigger than the carrier, so that's not going to work as either. So what it's going to do, number four, is going to do exocytosis. I can't draw it well, but it's going to get dumped by exocytosis. And number 5. Water moving from a cell's ICF into a highly concentrated saline solution. How does water move? Water moves down water's concentration gradients. If water is moving across a selectively permeable membrane and the solute is not moving, then number 5, water is going to move via osmosis. Okay, that is going to be osmosis. There could be an aquaporin involved or not, depending on where it is. Okay, and then last but not least, number 6. Calcium is being pumped into the calcium-rich extracellular fluid to allow for muscle relaxation. So what I have here is I have calcium, just in this instance, not always, low calcium here and high calcium here, okay? But I want calcium to go this direction. Will it go that direction just with diffusion? No, it's not going to diffuse that way at all. And can I get it to move through a channel against its concentration gradient? No, it's not going to move through a channel against its concentration gradient, but it will move through a carrier if you provide it with ATP. So that is going to be primary active transport. Even though we didn't do calcium transport before through a pump, so this is a primary active transport. A carrier plus ATP equals a pump. So these things in G that we're looking at right here, these are not things that I want you to memorize specifically. I want you to think through the logic that I just moved through and always go through the possible cheapest, fastest ways. And you need to be able to defend it if you are using a more expensive or slower way, right? Like, why didn't you use something cheaper? Okay. So this is just a little practice for you. It's not necessarily that I want you to memorize these examples. It's that I want you to understand the logic behind the prediction of each of these examples. And in the next video, we're going to put examples of transport into the human body. So it's no longer going to be cells. It's going to start talking about organ systems.